Today we will make progress and hopefully finish, even though I'm not completely sure, the proof of a theorem concerning spin correlations. Let me remind the statement of the theorem. So the setup is as follows. You take a domain of the plane, you discretize it by a square grid of mesh size delta. Delta is half the size of a square diagonal. And you consider, for simplicity here, plus boundary conditions. And you look at the expectation that one spin inside, let's call the point A, takes on this domain, for the Ising model on this domain, with plus boundary conditions at critical temperature. And the statement is that if you renormalize this quantity properly, meaning you multiply it by constant and you divide it by the size of the squares to the power 1/8, you converge as the mesh size goes to 0 to an explicit quantity, which is defined as follows. It's the derivative of the conformal map from omega to the disk to the power 1/8. And that's the result, okay? So, yeah, just a little back, something I find a bit funny about this result is that this, the fact that it should go to 0, like the mesh size to the power 1/8, is apparently a theorem of Onsager of 1944 or something, but I don't know anyone who has seen the proof of this result. I mean, there is a reference, but you cannot find this article online, and you cannot find it in most libraries. So I really don't know. Well, anyway, now at least we can use this kind of result because a stronger version is proven, namely that not only this quantity is bounded away from 0 and infinity, but it actually converges to an explicit limit, which was predicted by conformal field theory. Yeah, maybe I should have also cited John Cardy. He conjectured this formula in 1983, I think. Okay, so this is not exactly the statement we will prove. The statement we will prove in detail, and then we will give ideas about how to deduce the stronger statement from the weaker one. So theorem prime, we are going to look at the following ratio of expectations. So if you look at a spin at A and a spin at A plus 2 delta, they're essentially the same, which means that if you take the ratio, they should converge to 1. That's not very strong, but so you know you should subtract 1. And then if you divide that by the distance between the spins, so 1/2 delta, because that's the distance between the spins, you should get the kind of derivative. Well, namely, if you take things at the same denominator, you should get a derivative divided by the function itself. And that's indeed what you do get. So you get the x derivative of the logarithm of this function that was written here at x equals 0. Well, if you wish, it's the derivative over the function, the logarithmic derivative. Okay, so that's the result I want to give most details about the proof of. Okay? So the proof is fairly long, but I will really try to give all the steps, because each of them tells us something interesting about the model, or about discrete complex analysis, or more broadly speaking, about how we understand scaling limits of models, and that's precisely the goal of this series of lectures, to explain in a few cases how we understand this. So there are 11 steps. We'll start with a simple step, which is just a rewriting of things in a language of loops, just because it's more convenient for further notation. So let's rewrite things with loops. What do I mean by that? Well, again, we consider the easy model on the faces of this graph. So you have just plus minus ones on the faces. Well, let me remind that probability of a spin configuration is proportional to exponential of, say, beta times the sum over all pairs of adjacent spins of sigma I, sigma j, and beta for us is half log of root 2 plus 1. Okay. So the idea is that, okay, you have spins on the faces. Now you would like to just describe the spin configuration by the collection of all its interfaces. Namely, you're just going to put an edge between any pair of spins that is different. So write an edge, draw an edge, well, whenever the two spins on its sides are opposite. I mean, this is just plus, minus interfaces. These are precisely the kind of objects one describes with the SLE in the scaling limit. That's not what we are going to do in this lecture, but that's the kind of objects that one considers. So, well, what you get, tell you intuitively, is you get a collection of loops. Not necessarily simple loops. They can touch each other. Okay? That separates plus spins from minus spins. So you get loops if you have plus boundary conditions. Of course. If you don't have plus boundary conditions, you might get arcs that touch the boundary. Okay. So I guess that is not too complicated. And since the so now let's take a notation. So gamma is going to be the set of subsets of the collection of edges of the graph that form loops. Okay, and so you have a bijection between the plus minus 1 on the faces and gamma. So with plus boundary conditions. Okay. Okay, and you know, it's not very hard to see that the probability of a loop configuration through this bijection is going to be proportional to exponential of minus 2 beta times the number of edges in that loop configuration. Why so? Because you have an edge whenever two adjacent spins are opposite, and you have no edge whenever they're the same. Okay? So the energy, or these quantities, say, minus the energy, the sum of over all pairs of adjacent faces of the product of the spins, well, it's just going to be that you're going to add 1 to this term whenever there is no edge and subtract 1 whenever there is an edge. So just shifting this thing by an overall constant, you get that this term is minus twice the number of edges. And so exponential of minus beta to the power twice the number of edges just gives us this. Okay? Now, if we ask the question, okay, what is this quantity now? So define, let's call it Z bracket sigma A to be the sum over all contours in this collection gamma of exponential of minus 2 beta both edges. So that's essentially the partition function. I mean, that's the constant you should normalize this quantity by in order to get a total probability 1. That's not the quantity I want here. I want to somehow describe the average value of the spin at A. So how do I do this? How do I read the value of a spin at a given point in the loop picture? Well, take a point here. If there is no loop surrounding it, it just means it's +1, okay? Because nothing came in the way to change its sign. If there is one loop surrounding it, its sign is -1. If there are two loops surrounding it, the sign is +1. So it's really intuitive that it should be -1 to the power number of loops of omega surrounding A. So I want to define this quantity, and with this notation, what we have is that this ratio of expectation, so E of sigma A plus 2 delta divided is just going to be the ratio of these two gains. Okay? So this quantity is a function of A here. You count -1 to the number of loops in the configuration that surround A. Okay, so this ratio is that ratio. What is the reason? Well, this is essentially the expectation of the spin at A, except that you need to divide by the partition function of the model. But since you take a ratio here, you need to divide in both cases by the same partition function. So they cancel and you get this quantity. Okay? So that's just a preliminary step to rewrite a quantity in terms of loops. It doesn't look easier this way, but it will make things a bit easier in what will follow. Question? So now what we want to do is somehow to construct a discrete holomorphic function in the same way as was done for Smirnov's theorem that will give us, when we evaluate at the right place, the quantity we need. So first thing is that we will need somehow to deform our collection of loops, if you wish. So that's what I'm going to explain now. So deformation of gamma. So this is useful in order to make the contact with discrete complex analysis. So what is this deformation? So now let's decorate a bit our graph. Okay? So our graph so far is just a regular square grid like that. Okay? Maybe our point A is here, and we are trying to understand the point A plus 2 delta, the spin at the point A plus 2 delta as well. Okay? So now let's just add corners. That's not complicated. We just add things like that. So add 4 corners to each vertex. Okay. We are going to call them, whenever necessary, north, east, south, west. At distance, that's just for convenience of notation, delta over 2 from the vertex. So I just say that this kind of corner edge is of length delta over 2. And let me remind that according to our notation, the delta is half the size of a diagonal of a square. So this is half of the, that's half of this, that half. Okay, so now let's call for Z a corner. Okay. So a point here, or a point there, or a point there. Call gamma Z, little gamma Z, sorry, a path, any path, any, okay, going from a plus delta over 2. So we have fixed our spin that we're interested in. Okay, just to be more precise, I should have said that's the limit. It's not equal. Okay. So we fix our point A, and so A plus delta over 2 is this guy. Okay, this is A plus delta over 2. So going from A plus delta over 2 to Z. So let's make an example. Let's say if Z, going to need a color choke. So that's my graph. A is here, and say Z is there. The corner there. The path could just be something like that, okay? So it goes along the edges of omega dot. Okay, except at the very beginning and the very end, of course, A and Z are not vertices, so you need to make two little extra pieces to go from A to Z. A plus delta over 2 is Z. So, okay, that's A plus delta over 2. Okay? So call gamma Z a path going from A plus delta over 2 to Z. And now we're going to call by gamma capital Z a collection of pictures. It's going to be made of the following. It's going to be gamma Z, a little symbol I'm going to define now. Gamma Z exclusive or the symmetric difference with omega for omega in gamma. So I will just write A plus B like that for the symmetric difference, which means A union B minus A intersect with B. Okay? So what does it mean? Well, this is an example of a path in gamma Z. It's the exclusive OR of the path that I chose with the empty collection of loops. This is another example. Okay? So in this case, what I did is I took the exclusive OR of this loop of a single face, around a single face, with that path I chose, and I get a path like that. Okay? So we can say that gamma Z doesn't depend on the choice of little gamma Z. Okay. So basically, the collection of pictures that I'm going to get will be made of a path going from A plus delta over 2 to Z, wherever Z is. And potentially around this, you can have some loops. You can have some loops elsewhere as well. Okay. You can have some loops that will touch your path. That's still fine. Your path could, in principle, make a loop like that. That's still okay. Well, that's how this collection will look like. Okay? So there is no probability at this stage. It's just a collection of pictures, a collection of subset of edges, except that you also add two corners. Okay? So it's a function of Z, and it's also a function of A plus delta over 2, but this guy is fixed. Okay? we are not going to consider it as a variable anymore, at least for a long time. Okay, so now what we need to do is we need somehow to do something similar to what was done here. We need to sum over the pictures in our collection here a certain number. Okay, that's the goal. So let's explain how we're going to do that. That's a bit tricky. I think that's the trickiest part of the construction to explain. It's not conceptually extremely complicated, but it's very hard to explain. So we'll try to go slowly, and hopefully you'll understand if I make a lot of examples. So we are going to define. Let me write the definition and then explain what the terms in the definition mean. Okay, we are going to define. So a function f. I'm going to write things with some strange bracket subscript. F a delta z. Okay. I'm going to define it this way as so the sum over all little pictures in gamma z, just defined here, of something. It's going to be exponential of minus 2 beta times the number of elements in gamma, the number of edges, full edges in gamma. So that's still not so hard to guess. I mean, it's the same as here. The collection of pictures is the one that has changed at this point. Minus 1 to the number of loops of gamma surrounding A. That's still exactly the same as there, except that in those pictures now, we don't only have loops, we also have a path. Well, this path doesn't count as a loop. Simply, you just look at the rest and ask how many loops are there. And now there's going to be 3 more terms. We're going to add a complex number, exponential of minus what we call the winding, we should call it the turning of the path from A to Z. I'm going to explain what this means, plus a sine term. So I need to explain all of these terms in details. That's going to take some time. And we divide all of this by Z sigma A, the term I just defined there. Okay. So this really is the analog in the proof of Smirnov's theorem of this complex linear combination of probabilities. It is the object that will pass to the limit. Okay, it's a much more complicated object to define, and it has a less obvious probabilistic meaning, but that's really, still the key ingredient. Proved in the same way as this function is a key ingredient. Okay, so let's explain what things means. So definitions. So number of edges of gamma, the number of full edges. Okay, the corners don't count. That's easy. Number of loops, what I said. Number of full loops surrounding A. Okay. W of gamma, that's the winding or turning number of gamma from going from A to Z. Z. And so it means ignore the loops. Okay. So we should just look at what links A to z, or a plus delta over 2 to z. Let me be precise, so a plus delta over 2. So what is this number? It's a measure in radians of some angle. This, for instance, is if a plus delta over 2 is here and z is there, the corner next on the east of a vertex there, the winding is 0. Now, if your path does this, for instance, the winding, how much have you turned? How much has your tangent turned to go from here to there? Minus 2 pi. If you get something like that, for instance, if your z is on the south, is on the north of a vertex, your winding will be pi over 2. Okay, if you do something crazy like that, for instance, what is going to be your winding? 2 pi, 4 pi, 9 pi over 2. Okay. Well, it's okay. And finally, this is the hardest somehow to I mean, this makes it harder to do everything. So I have to confess I cheated a little. Z, I said, was a corner. But I didn't say what this guy was, and that's somehow related. So Z is a corner of omega delta A, but I didn't say what this guy is. That guy is not exactly the same as the omega delta. The pictures, gamma z, are exactly the same. But this is a bit different. What is it? It's a point on the double cover of the graph. So is the double cover of omega delta ramified around A. What does that mean? What that means is the following. So this idea of ramified cover was introduced to understand square roots. And I believe everyone who has studied in Russia is very familiar with those things. That's how you construct a square root in Russia. But that's really not something that's super standard otherwise. So what is the double cover? So it's basically is the collection of that you obtain if you take all the z's in omega delta in the regular graph, but z with a prescribed value of square root of z minus a. Okay. So A is again the center of the face here. So think if A was 0, for instance. If A was 0, what would all that mean? So if you know that, okay, you define the on the positive axis by convention, you define the square root to be positive. But when you are in high school, so at some point you wonder why the square root is not, square root of 4 is not minus 2. Well, it's just by convention that square root of 4 is not minus 2. But in some sense, square root of 4 is also a bit minus 2. And the sense to make the way to make sense of this, if you want to make the square root a continuous function, is to say, okay, we are going to say that now in the complex plane, well, you want to define the complex square root. In the complex plane, there's not going to be one, if this is 0, there's not going to be 1 point here, there's going to be 2 points. Let's call one to be 1, and the other is 1 prime. Square root of 1 is 1, and square root of 1 prime is minus 1. And this way you can move continuously on the on the plane, and once you make a loop starting from 1, and you arrive here, you arrive to 1 prime. Okay, that's really what you obtain if you try to take the square root and make it continuous all the way. When you come back here, you change sign. So the double cover is somehow a surface that has 2 points living above each original point, and such that each point on this double cover has a prescribed square root. So if you ramify around a instead of 0, then you just prescribe the square root of z minus a. That's it. So, okay, that's what it means. So z is now not exactly a point of omega delta. It has a bit more information. It's a point of omega delta with a prescribed value of square root. So we can still identify it whenever needed with the point of omega delta, and that's what we do here. Okay, the z here is the same as the it lives on omega delta, but here the z is a bit different, and that's related to this term. So now one more thing is that every point has to be upgraded, if you wish. Every point has to know now its square root. So we choose to upgrade the other corner, a plus delta over 2, such that, well, the square root of a plus delta over 2 minus a is positive. Okay, this guy is just on the right of a, so the natural choice is to take a positive square root. And now one more remark, it's crucial. If D is a subset of the double cover, of the simple domain, minus A, so it doesn't contain A, that is simply connected So, you know, now the square root is not somehow well defined on the plane. It's defined on this double cover. Now you can ask, okay, at a given point, on which sheet is it? Well, it turns out you don't have a really simple way to say there's one sheet and the other. I mean, it's easy to say there are two sheets. There are two square roots. It's hard to say which one is natural, more natural than the other. But however, you can say that 2 points that are close by have the same kind of square root. I mean, they're either almost opposite or almost opposite or almost the same. So if you have a simply connected domain that doesn't surround the origin, it makes sense to define SD, let's call them CD for, so CD in the double cover, but also in the domain. We can define this to be plus or minus 1. Plus 1 if C, D plus are on the same sheet. And minus 1 if they are on different sheets. Well, if you wish, you can take a branch cut in the complementary of this domain and define sheets according to this branch cut. Okay. Of D. Over D. Sorry. So, for instance, it's hard to explain this very easily, but for instance, a standard simply connected domain that doesn't contain A is the cut disk. Okay. So now it makes sense to define whether 2 points here are on the same sheet or the opposite one. What you would do is imagine if this point is 0, you could just take the ratios of their square root and see if it has positive real part or negative positive real part. And it will tell you whether they're the same or different. Okay, so now what we do here, and we say, well, okay, of path, is a simply connected, or it can be made simply connected by filling some things that doesn't contain A. And we can decide, you can add a plus or minus 1. So I think I have defined all the symbols, but that's, that's not completely straightforward as a definition. So let's make a few examples of, the values of this function. So let's call the whole thing, let's call it capital W of gamma. Okay, that's a number that we associate with any configuration. So let's make a few examples of this. I'm sorry I cannot really draw the square root on the blackboard. If you're still around next week, I'll show a slide where there's a picture that explains a bit what the square root surface is. If you have not seen it, you can also look on the Wikipedia. I mean, there is a nice picture of the square root surface there. It helps understand what happens. So anyway, for instance, what is, say, if this is, oops, sorry, if this is A plus delta over 2, this is Z, so the outer loop is my domain, and I have some things like that here. What is the weight of gamma? Okay. Well, it's going to be e to the minus 2 the number of edges. I mean, you just have to count the number of edges. That's easy. And then there's the number of loops. So minus 1 to the power 1. Here there's just one loop surrounding A. Time 1, okay, times, what else is there? There's a path that goes from A to A plus delta over 2 to Z, and what is the winding of this path? Well, you go here, this point you have made no turn, here you make a minus pi turn, here you make a minus 2 pi turn, and you add an extra minus pi over 2, so e to the power 7 pi I over 4. Because I take minus the winding I times over 2. So e to the 7 pi I over 4. And then plus minus 1, well, again, on this picture, I have hard time drawing the specified square root, so it will depend on whether Z is on one sheet or Z is on the opposite sheet. Okay? So that's what this function is about. Now, just a little more thing, extra thing. So we can define f omega delta Z on midpoints of edges. Okay, so things go exactly the same way. So if Z is if Z is a midpoint of edge, well, you can still define a collection of a path that goes from A to Z and just stops at the midpoint of edge. Count loops in the same way, define all these things essentially, in 100% the same way. There's only one difference. So define the same, except for a 1 over cosine of pi over 8 prefactor. Okay, so I just want to be rigorous in my statements that I will need the function defined on the midpoints of edges, but it's exactly the same definition except that you add a 1 over cosine of pi over 8 in front. Okay, so now what do I want to do with this function? Well, the first thing we want to do is understand why on earth it can be relevant to study all quantity. Okay, and so I'm going to show that now. So useful value. So we do exactly the same as in the proof of Smirnov's theorem. Exactly an exact analog of the operation. We look at boundary conditions and we learn something useful that happens on the boundary. In our case, the boundary has two parts. One is around the face A, that's a kind of boundary, kind of special thing happening here. And the other is the outer boundary. So a useful value So f omega delta a at a plus 3 delta over 2. So where are we at this point? This is a plus 3 delta over 2. Okay? So our function is a function of any z that's a corner or even a midpoint of edge. Now if I evaluate it at that corner, which is right in front of the corner from which the path starts, what do I get? Well, I get something that's nice. I get a ratio of expectations. Yep. So that function I constructed is very complicated, but at some points the values are not that complicated. And in particular, at one point it's exactly what I need. And then you can ask me, okay, actually, on which sheet does this guy live? And well, the answer is that a plus 3 delta over 2 such that its square root minus a is positive. Okay? You always have to specify if it's the point or its nemesis or somehow. Yeah, the point on the other side. Okay? But so somehow this a plus 3 delta over 2 is the guy that is on the same sheet as this guy. Okay? So that is useful. So boundary conditions. So the first thing that we should say is that at z equals a plus delta over 2, if you take z here, it's not very well defined. What does it mean, a path that goes from the point to itself? We shall not define it, okay? So that's our boundary condition, so we don't define it. At least not for now. That's okay. And now on the rest, well, something nice is happening again. So I said you can define the function on half edges, on midpoints of edges, sorry. So on this point. Okay, z can be one of those points. Now it turns out that you can extend somehow your domain just a little bit by adding half edges on the boundary. Assume our domain is just a trivial domain made of 2 squares. Now let's just add half edges and say, okay, these are also valid points at which the function could be evaluated. And indeed, that's the case. You can define everything I defined here. You can perfectly well define that for the boundary edges. You can about boundary half edges. You can have a path that goes from A to Z, which is a boundary half edge, and yeah, I mean, that poses no problem, no specific problem. But it's good because it's a boundary and it has boundary conditions. It's not a cause of problem; it's a cause of convenience. So let's say what we have. So extend to boundary half edges. And to extend to boundary half edges, and for each we have boundary conditions, and for each z midpoint of edge xy, an oriented, say I orient the edge xy. No, I don't orient. I just say the edge xy where x is in the domain and y is not. Okay. If you're a boundary half edge, you are linking a vertex of the domain with a vertex not of the domain. Okay. this edge goes somewhere outside the domain. This is x, this is z, this, let's call it z prime, and this is y. Okay? So what can we say? We can say something about the value that f takes. What we can say is that f squared omega delta a z times y minus x, so you identify, of course, the points with complex numbers, is positive. Okay. So that's a fairly strong condition because our function is complex. So it tells us that we actually know the argument of the square of a function, which means that we know the argument of a function up to pi. You know? Okay. So that's a nice boundary condition. Okay. So I should prove that in principle. I'm going to prove the other guy. This proof of this guy I'm going to just give a hint, and with the hint it should not be a hard exercise. Proofs. Okay. So why do we have that the value here satisfies that? Well, I will not really prove it rigorously. I will just make a few pictures describing various configurations, various things that can happen to you, and explain why in each case it's good. Sorry. Again, this is A. This is A plus 2 delta. This is A plus delta over 2. This is A plus 3 delta over 2. So there are a few cases if we look at spins living on the Ising model, and we try to understand that in connection with this definition. The first thing we see is that, okay, we at least have the good denominator. We just need to check that the numerator is the same as this guy. Now, that's the first thing. So let's just focus on the numerator. And what can happen in terms of Ising configurations? Well, these spins, well, obviously they're either the same or they're different. And if they're the same, it's for some reasons, and if they're different, it's for some reasons. So what can happen between two adjacent spins? Well, you know, they can totally just be not separated by anything. They can just have the same sign. Here there's no loop, okay? They have the same sign. This is A and A plus delta, 2 delta, same product, same value, okay? So now what can happen is that A and A plus 2 delta are such that A plus 2 delta happens to be surrounded by a pi. That's a different value. What can also happen is that A is surrounded and A plus delta is not. It's also a different value. And the last possible case is that they are both surrounded by loops that don't have much choice. One has to pass here and the other has to pass here. Okay. What we know is that if we try to define a function at A plus 3 delta over 2, well, we can just take this collection gamma at A plus 3 delta over 2 by adding on top of this a little extra path that will just do this. So let's just do this. Let's just take a collection of loops and add this extra path. Now it makes it a valid picture to be evaluated into that sum. So how do we evaluate it into that sum? Well, we see what we get. So basically the first thing we notice is that we still count the number of loops surrounding A. So somehow we are keeping track of the value of this spin a priori. Now if by chance the rest of these terms these two terms, somehow tell us if these two terms tell us the value of the product of the two adjacent spins, then there's going to be a simplification with the first spin. It's going to appear as a square, and it's going to be 1, and we are going to win. So that's the idea. So want to prove that exponential of minus I winding times the sheet term delta over 2 is equal, through the loop correspondence, loops of Ising, to sigma A plus 2 delta. Okay, this way, right. Thank you. This way, since -1 to the number of loops represents sigma A somehow, we will get sigma A times sigma A times sigma A plus 2 delta. And of course, these things being plus minus 1s, if you square them, they cancel. Okay, so what you need to do is check that in each case. Let's just do one case. So the case where there's nothing, obviously that's easy. I'm not going to do it. If the path goes straight, the winding is 0, you don't change sheet, nothing happens. Now the thing that becomes more interesting if, for instance, you had a loop for the Ising model, and you had this little path. How to interpret that? Well, the idea how you should interpret it is that whenever you arrive at this point, you decide that your path must either turn left or turn right, but not go straight. So let's say that whenever there's an ambiguity, we turn left. So that's what happens. Okay, so here what happens is that we are doing what? We are not changing sheet because that's A. We are not changing sheet because we don't make a loop around A, but we are doing a winding. We're doing a winding of minus 2 pi winding. Doing a winding of minus 2 pi, plugging this into here, gives us a minus 1. So it gives us an extra minus 1 on top of the rest of the number of loops. So it tells us this spin is different from that one. So one more case. Now if it's just this way, A, C. So what do we get here? Well, we do also, we also have some winding here, and we go there this way. So now it's a bit more subtle. The idea is that we should not count this as a loop because it's part of the path. Because so we lose a minus 1 that we should get for the spin, but at the same time, because we make a loop around A, this is where this term will enter the picture, and we will change our sign. We'll cancel the loss of the loop, and then the winding number is going to be minus 2 pi, like in this case. So we are going to be fine. So well, plus other cases. You can check that in each case you get the right thing. Okay, so what can we do now? We have boundary conditions. So say this is an exercise. It's fairly easy. So check for every configuration. The idea is that, okay, you have an identity saying something about the argument of the function. Forget about the square. Just saying that f is a real multiple of 1 over square root of y minus x. So we have a linear condition. And if we look at the definition of the function, well, if each of the terms in the summand satisfy the linear condition, then the sum obviously satisfies the condition. This is real, so it will not affect at all the argument. So you can just check by hand that every picture contributing to a boundary term will have the right inner condition in order, which will allow you to get this. The last thing, as usual, that's the hardest, at least the hardest to find. Last thing, but not least, is the analyticity. So what do I mean by analyticity? I mean some discrete Cauchy-Riemann is satisfied. And in our case, it comes across as a fairly peculiar, in a fairly peculiar form, in the form of S holomorphicity. I have to define what this means. But the statement is that the function, as a function of z, as a function of the extra variable, is discrete holomorphic in some sense, so it should be expected to converge to a continuous holomorphic function. So, what is S holomorphicity? So, definition: a function f. Well, let's take our example at hand. This guy, 2c, is S holomorphic if S is for spin somehow. So is S holomorphic if for any pair, let's call any any pair CZ, C a corner adjacent to a vertex V incident to a with mid edge Z incident to an edge whose midpoint is Z. So what do I mean? I mean something really simple. So you have neighbors essentially. So there's a relation between values at neighboring points. So this is your graph. Z is a point here, V is a point there, and C is there. Okay. So C and Z are adjacent. It means that they share a common vertex, which we call V. Then we have this relation f of C equal to 1/2 of f of Z plus complex conjugate of C minus V f bar f of Z. Okay. That's the condition. Well, I mean, it's a condition. It's clearly fairly strong because we have as many relations as we have pairs of corners and adjacent edges. It's not really clear where is discrete holomorphicity at first, right? But you have to believe somehow. So, so it can be shown to imply things like, well, that's not very precise, but if you call this guy northeast, southeast, northwest, southwest, f of northeast minus f of southwest plus I times f of northwest minus f of southeast is 0. Okay. So it's not completely obvious, but it's not completely hard to prove it either. Basically, here you have four midpoints of edges. There are four corners separating them with four vertices. This satisfies the relation with that, and this satisfies the relation with that. So this and this satisfy some relation. 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 And if you just rewrite these linear relations, you take a linear combination of these four linear relations you obtain, you just get that equation. Okay, so that's an exercise. Okay. So another exercise is that this function does satisfy this relation. It's not completely straightforward. With this definition, it's fairly easy. Exercise. F omega delta A is S holomorphic on omega delta A, except at A plus delta over 2, where we have not defined it. Okay. So hint, because it's not completely straightforward, construct for Z and C, V as above. Construct the bijection, which we are going to call phi ZCV, that sends a configuration gamma to gamma XORed with the quarter edge CV XORed with a half edge VZ. Okay. Symmetric difference. In that sense, gamma C to gamma Z, and gamma Z is an involution. Okay, and the statement is that the complex weight of a configuration and of its image phi CZV satisfy the relation. Star. Yeah. So the idea is that how you prove it is you prove again that each term in this sum satisfies the relation if we map a term of the first sum to a term of the second sum by this involution. Okay, so that's almost where we're going to stop now. I'm not going to write further, but I'm going to explain what's the strategy then and what we have done at this point. What we have done is we have constructed a complicated function here, living on the double cover, such that if you evaluate it at a certain point, it gives us the quantity we want. This function is discrete holomorphic, that's the last statement, has boundary conditions dealing mainly with its argument on the boundary. And basically, that's it. So there is one statement which is, I think, very hard to prove, even though it seems just a linear algebra statement, which is that the function is uniquely defined by this condition. So in some sense, we can completely forget about the Ising model. In practice, however, we can't, because we will need some extra insight from the Ising model. But at least it's satisfactory to know that we have reduced, in principle, a quantity to a quantity rising from the solution to a collection of linear constraints that has a unique solution. So the plan then will be to show that this function, renormalized essentially by 1 over square root of the mesh size, will converge to a continuous holomorphic function, completely explicit. And then we will do a Taylor expansion of that holomorphic function. And the second term in the Taylor expansion is going to give us precisely this derivative that we wanted. Okay, so the plan is I will make a statement. The function converges. We'll give the main ideas of the proof of this statement because I think it has some insight into what happens, and then just read the continuous solution, read the information we need from the continuous solution, and obtain the proof of the theorem. Okay, so that's it, and then I will just briefly discuss a study.